There we go. We should be on. Right. So should we crack on then? Right. Well, welcome back. This week we're going to do some more reactor design stuff. So the follow on from the Tokamaks we did last week, we have a look at some alternatives to Tokamaks this week. So let's just right. So that's what we're up to. So week 4 of 12, so third of the way through. Still up to some change if you want to add in stuff or take stuff out or whatever you like. But this is what we've got at the moment. Just to note that tritium breeding won't be next week. Radiation damage won't be next week because Charlotte's not available to do that lecture, so we just swap. So today, yeah, we're going to keep on with looking at some plasma physics and into reactor design. Going to have a look at Stellarator, basic principles of ICF, inertial confinement fusion, some different designs of them, do a little bit on Tokamak versus ICF, and then also we'll have a little touch on alternative fuel types. So actually, this happened just before last week's lecture. I almost put it in, but I didn't. But you might have been told about this yesterday if you were on the trip. But MAST, which is the mega amp spherical tokamak, did something really good the other week. They managed to use their magnets to create what they call a 3D magnetic field. Don't worry about what that means. But generally, it's the first successful control of plasma instabilities in spherical tokamaks, which is very important because there's these things called ELMs that happen, which we'll probably talk about later. But the easiest way to imagine them is like in the sun has solar flares, where they just randomly spit out loads of plasma. That sort of happens in fusion plasmas as well. So controlling these where you can have like multiple orders of magnitude extra heat just being thrown onto your reactor wall is really important. So they've actually managed to do it. If this link works, we might be able to see it. You'll have to tell me online if you can't see it on the correct screen. Let's put that over there. Sorry, it's only on LinkedIn. I couldn't get it to embed in the PowerPoint at all. But here's a video of it. So yeah, it's pretty cool. So that's a video of their plasma being on for a couple of seconds. I remember you can only see the visible, you can't see the video. Oh, for Pete's sake. Technology's shit. I mean rubbish. Hold on, let me stop sharing and share the particular screen. This should be the only one that I need to do this for. I know, I'll just do the entire screen. There we go. Right. So you should be able to see that now. But yeah, so it's showing them suppressing the elms, which is probably that big. Can you see that now online? Yes, no, maybe, otherwise. Yeah, cool. Right. So we're done with that. Right, let's carry on with the actual lecture. Well, did you enjoy Jet the other week or yesterday? Was it good? Did you learn anything? No? Yeah? Were the lectures helpful in preparing you for that or not? No? Did you feel like you understood a bit more of what they were yabbering on about? Yeah? But it's cool, isn't it? We can have a talk about that later if you like. But yeah, so this is where we failed last week. I'm going to attempt this, and if it doesn't work, we're going to just do it properly. So, come on. Yes! Right. So please log on to the just www.classpoint.app and then use that code to join in. And I'd like you to answer the question of, come on, move out of the way. So you still should be able to see that. I would like you to just remind me what a diverter does in a tokamak and what sort of musical media storage do ITER's diverters replicate. So online, you should also be able to sign in for that as well. Let me know if you're struggling. And if this is a rubbish survey app, then I'll just swap to a different one. Or if you hate surveys and lectures, I can just remove them and we can try something else. But if you want to have a crack at the question, feel free. We got any answers yet? There are no participants yet. Oh dear. Is there anyone struggling to get on it? For peace, we got so close. Oh, well, someone's managed it. All right. Well, you know what?
Probably use spend next time.
Yeah.
Or
Yeah. Okay. Right. Well, I'll use Menti then. I'll get the picture. Right. Let's get rid of that then. Okay. So I'll take hands up then instead. Or just shout it out. So what does a diverter do in a tokamak? Anyone remember? No? Yes? Go on.
remove the error.
Correct. Yep. Removes the impurities in the plasma. Any ideas of what musical media storage I'm on about? No? Yes? Imam will know online. No? All right. Well, so yeah, it's the exhaust essentially, extracting some heat, plasma impurities and spent fuels, and eaters mimic cassettes, which pop in and out. Don't know if anyone here has ever owned a cassette, but I mean I have, but like okay, cool. Right, so let's crack on to actually what we're covering this week. So this is a Stellarator. So this particular one I'm using as example is Wendelstein 7X. So it is still a toroidal shape. It's very adjacent to the Tokamak stuff. But instead of having a central solenoid and then ploidal and toroidal field coils, it has helical and toroidal. So two sets of magnets wrapped around the same shape. They don't require a central solenoid for startup. So generally, this means they have more space for other equipment and stuff in the middle. And then they're more stable generally as well. That's why they're favored. Their plasma stability is much better. However, they've got a very complex geometry, especially in the magnets, which makes manufacture a lot more difficult. And their magnet space basically being wrapped around the whole thing means that it's much harder to design tritium breeding and control systems to sort of jam in there, which is why you see like millions of ports just sort of on the top of that picture there, just sort of every which way, because they're just trying to fill any space they can, but they've not got much of it. So generally, you don't see much Stellarators because it's higher complexity means higher cost. So historically means people have just gone for more standard tokamak designs in their experiments because it's cheaper. That sort of is the defining factor for a lot of research in general. So they're just not as popular at the moment. So here's an example of a magnet shape from a previous iteration of Wendelstein. So you can see it's not, well, it's quite funky. So we'll carry on with Wendelstein. So currently it's the largest accelerator experiment in the world and it's in Germany. It's built of basically almost 5 nearly identical sort of modules sort of clipped together. And you can see the sort of magnet plasma schematic at the bottom there. So you can see that the plasma is twisting on itself as it goes. So their goal is to create sustained stable plasma, and their current record is 43 seconds of high performance plasma, which is essentially fusion plasma this year. Their target was is basically 30 minutes, I think, long-term plasma, which if they manage it would beat the current record for Tokamaks, but they're currently nowhere near. This particular experiment only uses deuterium, basically to reduce costs and radioactivity slightly, because tritium is radioactive and it's very, very expensive, and it aims to run hot enough to achieve fusion plasma. We'll go on to that a little bit later, but generally means much hotter. So some milestones for it. In 2015, it began operation after sort of being penciled in the 1980s. They managed to do hydrogen plasma in 2016 for a quarter of a second. They achieved the fusion triple product. For the intensive purposes of this is essentially a good plasma for fusion. And then they achieved the world record of that in February this year. And then they took it down for maintenance until August 2026 for upgrades to go for higher power and longer duration. So here's an example of their water cooling system in the picture at the top. Very complicated because the whole thing's a mess. They're magnets. They use a lot more magnets. So you've got sort of 50 non-planar coils and 20 planar coils. So 7 different types of magnets. And they all have their individual power controls, each type. Basically gives them much greater plasma control to the point where they actually can't give you a proper 2D picture of it because it's just so complicated. So I didn't bother putting that into this because I wasn't going to explain that. The heating, they use high power gyrotrons and then resistance heating, which we talked about in the previous lecture, which throws about 15 megawatts of energy into the plasma. And then they also use some neutral beam injection, like we talked about with ITER, to basically get it to that extra step to get it to the fusion plasma level. Generally, it's water cooled, but for the magnet systems, you use liquid helium. So you can see sort of a time versus cooling for the magnets there. Starting from about room temperature, which is 300 Kelvin-ish, going to about 4-5 Kelvin on the bottom. I throw that in. It's approximately costed €1 billion, so it's not cheap. And MancheSTAR visited it this year, so I guess I don't need to do a person for scale because you can see it. Yeah, so he visited it like he visited Cullum the other day, or yesterday. So hopefully it might be on the cards to go again sometime. So ICF is the main one, it's the main alternative. So Stellarator is sort of the cousin of the Tokamak. This is like just complete divergence. So what if we didn't use magnets for controlling plasma at all? If we just didn't have any of them? So it would lower the cost massively. You wouldn't have to do any cryogenic stuff. You'd lower the input power supply. The reactor would probably get quite a lot simpler. But how do we actually get sustained plasma without any control? The point is we don't. So this is what inertial confinement fusion essentially vibes with. So the idea is you run a power plant with a repeated implosion of your fusion fuel, and you collect your energy in bursts. With enough frequency of implosions, you sort of get a steady state of operation. So the general sort of way of looking at it is a tokamak is more like a furnace, it's on constantly, whereas ICF is more like an internal combustion engine where you've got lots and lots of implosions leading to a sort of steady state operation, even though it technically isn't. Most of the ICF sort of experiments started in the military, partly because the actual physics of it replicate a proper nuclear bomb. So we can talk about that with NIF in a minute. So the idea is you have a pellet about the size of a pea of your deuterium-tritium fuel or your deuterium-deuterium fuel. You generally fire lasers at it. That's the most popular way of doing ICF. You fire it at your pellet every which way, symmetrically. Then the outside will get rapidly expand and blow off. This will cause a compression into the pellet, which will then lead to an implosion. And then you'll get your ignition by fusion fuel because the force of the implosion is enough to make it super dense, so it'll ignite, and then you'll have your thermonuclear burn and your fusion plasma. Although it's not technically a plasma, it's just fusion explosion, essentially. So there's two ways they generally do this with the lasers. You've got direct drive or indirect drive. So direct is on the right and indirect is on the left. So you generally need a sort of symmetrical laser sort of focus on it, and then you'll get your implosion. So direct drive is just fire lasers straight at the thing, whereas indirect drive, which is more popular for sort of power plant design, you'd have this thing called a hull round, I think it's called, where you fire it in. This could be a very high Z material, so you're looking at like gold or something like that. This will basically be irradiated by the lasers, produce X-rays because of the amount of energy, and then those X-rays will have the energy to then deposit into the pellet and ignite the fuel. So, any ideas so this is our fusion cycle we had last week. Any ideas what the difference for sort of a power plant running for ICF would be to this sort of diagram? Any ideas? No? What would the difference be if I drew this diagram for a reactor which used inertial confinement fusion? So for online, you're saying that there won't be tritium coming out to then reuse for the next go. To be fair, it's a bit of a dirty question because generally we're going to skip that. The only difference is there's no plasma confinement, but the rest of it's pretty much exactly the same. So it was basically a trick question. I'm sorry, but you don't have a constant plasma flow. But you still require tritium production if you're using tritium fuel. And it's generally the same. And it's generally sort of similar to how Tokamaks run. So the only change I'd actually make to this is calling it a vacuum chamber rather than a plasma containment, and then I just sort of have it pulsing instead of constant. But that's generally the sort of thing we're looking at for these. So let's move on to NIF, which is essentially the most important thing when you're looking at initial confinement. It's sort of the main front runner for a lot of the stuff that initial confinement does. This is the place where they had the first scientific net gain from fusion ever. So this is one, I don't know if you remember in the news, I think it was a few years ago now, where they did a successful implosion with their plasma, with their lasers, which then got them a yield out. So they got current record of lasers giving 2 megajoules of power and yielding 8.6 megajoules. The engineering gain is still negative because the amount of energy the lasers draw. So it's not actually a full engineering positive, but it is a scientific positive. They use indirect drive, which we saw on the other page. And if you've ever seen Star Trek Into Darkness, which is the second new Star Trek film, they use this as the warp core. So the warp core for the Enterprise was actually just this. They were just walking around this as if it was in space. I just thought it was cool. But yeah, so this is a list of some of their previous experiments. So you can see in red, you've got the laser energy and then the fusion energy out. This is not connected to the grid, by the way, but you can see sort of the trend is going upwards. Well, I can't remember what the experiment was for their 9th run. And I just can't remember why it's so low. But you can see you're getting about 4 times as much fusion energy out as you're intending to put in. This is sort of what it looks like. So when it's not in Star Trek, it looks like that. And then the interior, where you'll actually where you'll focus all your lasers to, is like that on the right. Yeah, it's a big piece of kit, very, very complicated. And like ITER, we can have a look at what this sort of plant looks like. This is a military experiment, essentially. But some of the plant operation will be similar to what this looks like. So it looks a lot smaller than ITER. So you've got your sort of chamber at the bottom, and you've got all the different diagnostics, conditionings, assembly, all that. The big scientific complex. It's pretty cool. So just a bit more like numbers. So generally they aim to have 2 megajoules from their lasers. They have 192 different lasers going into their whole RAM using indirect drive. They make theirs out of gold, although you can use silver or platinum or something like that. The fuel loading is direct for this one. So this is just they'll put some fuel in, run an experiment, but they're not going to try and do consistent power plant running. That's not what it's made for. For real ICF, generally sort of there's a few ways of doing it, but generally sort of you'll use pneumatic pellet injection, planned at a pulse rate of at least 6 times a minute, so that up to like 1 a second. So these things like can be rapid fire, which is potentially a problem because this is quite a complicated bit of machinery, and you want it to be firing a laser, producing power output multiple times, maybe once a second. So it's quite complicated. And the main thing is to have a look at with NIF is their lasers are about 0.5% efficient. More modern lasers, if they updated them, would be closer to 20% efficiency, which would take us a lot closer to getting engineering gain out of this. But because it's a military installment, technically, upgrades are not easy to do. They don't really want to change them. They want to keep it so they can keep making similar weapons. But yeah, so that's what NIF sort of looks like, what you have in lots of lasers. The next one, so ICF is crazy because there's so many different ways of doing it. So I've just picked 3 examples. So I've got one, NIF is the most standard, and I've got 2 other ones which are a bit weirder. So it's based near Oxford. It's a private company, so it's not the UK AEA. They sort of focused on advanced target design, which is the target being your pellet. Does not use lasers at all. They focus on shockwaves instead. So they've actually tried to make this gel, which is that picture on the top, where you have it'll fire something at this gel, it'll create a shockwave symmetrical around it to then hit the pellet at the same time and cause an implosion that way. It's a lot more complicated. They've had very limited success, but they initially had a power plant design, which they've since rescinded. but the YouTube video still exists, so I thought it was worth a look. So this is an example of what they thought they were going to do for their power plant design. Oh no, come on.
Build a website.
It's just started on my actual laptop as well. No. There we go. Right, let's try that again. So here's sort of what they're doing. It's 50 meters tall. Here's where they actually load the thing they fire at the pellet at the top. At the bottom, you can see the little white cubes going in. That's the actual fuel. Any ideas what this liquid is? Any guesses on what it would be? Anyone? No?
Yeah.
Lithium? Correct. They want a liquid lithium shower in their reactor with a metal containment vessel. So this shower is meant to absorb all the radiation and also act as your breeder blanket at the same time. So you have it. So this one's done in about 20 seconds, and then they reload and go again. Surprised that actually worked. No. So, well, so you drop your fuel in, you fire a pellet at the fuel, that gets amplified and implodes, and then your liquid lithium will hopefully catch all that energy and heat up, and then that'll be extracted via pipes, along with your tritium that will create. So they might try and do two things at once. This is a massively flawed reactor design, and we can rip into it later. But it's just an example of how different ICF designs can be. But this is perhaps my personal favorite of how crazy some of these are. So this is General Fusion in Canada. They use pneumatic pistons to compress their fuel. Another one that's laser free. So if they use the pistons with enough force, they can simultaneously create an implosion. They're currently building a variety of different test machines for different aspects of their fusion power plant design. Currently, their goal is only to do a 70% scale pilot plant, just as sort of proof of concept. Their main idea is to have about 500 2-meter long pistons and only use deuterium fuel. And the reactor design is surrounded by a vortex of liquid lithium, sorry, and aim to blend elements of some of the Tokamak designs into ICF. This one is backed by Bezos, so I don't know whether it makes you more of a fan or less of a fan, but the investment's there from coming with people with a lot of money, and they've successfully produced a magnetized plasma for their injection system earlier this year. So, come on. So this is an example of sort of one of the things they're trying to test. So this is a ring of lithium that they've actually managed to compress using their subsystem. You can see it's compressing there. So there's no plasma here. There's nothing like that, but they're just basically proving their piston system works, and they're using it to inform future experiments from future designs. So, come on. So this is sort of generally like what they look like. So I couldn't get a better quality image. This is the best one I could find. So you've got your many pistons on the outside, and a sort of almost spherical Tokamak shape in the middle. But there's no magnets to get in the way. You have your liquid lithium lead flowing around the outside and a plasma injector at the bottom, basically to sort of kickstart what's going on. And then you'll have your fuel in the middle and it bang. And then you'll have your sort of ICF type running. Very cool. So generally, ICF, the companies are more agile because they're much smaller and cheaper. So they can sort of make a reactor or test bed, test it, break it, whatever, and carry on. They haven't wasted loads and loads of money. So it's much cheaper. There's no magnets. Generally, it's sort of, well, maybe I shouldn't have written this, but it's sort of simpler to operate because you don't have to actually worry about plasma confinement. But at the same time, you've got a lot of mechanical components which could go wrong, especially if they're in presence of a lot of radiation, lots of temperature, and they're also moving quite quickly. So it might be difficult. Technically, it is the only proven form of a positive scientific Q factor. It's not just theoretical like with a Tokamak. However, it's more difficult to produce a more consistent power load, more difficult to produce tritium if they need it. There is a massive nuclear proliferation risk with a lot of these, seeing as especially most of them, the experiments were designed for creating nuclear weapons. So that needs to be kept in mind. The technology is often less proven. I mean, I don't know if you've ever seen them trying to implode something with a load of pistons, but I certainly haven't. Although cool as it is. And there's generally a lot lower international collaboration due to both military stuff, and you'll see a lot of private companies going this method because it's cheaper with a potential massive upside. They're generally not governments doing these kind of stuff, although sort of do, but it's less like STEP or ITER or things like that. So we're just going to have a quick touch on some alternative fuel types. So we have mentioned deuterium reactions already. So tritium technically isn't required for fusion because atoms smaller than iron will fuse in stars, right? So it's actually possible. You could technically run all the way up to iron and do fusion. So can we take advantage of this? We're not going to do the survey, but any ideas what this graph is actually telling us? So we've got temperature on the bottom. We've got a rate coefficient, which for intensive purposes, this is how much energy you get out. We've got DD there, DT, deuterium and helium, and that's proton and boron. So any ideas what this graph is really important for us for? No? It's okay if you don't. I'm just asking just to make you think a little bit because I just natter on otherwise. So this is showing all different fuel types. These are the main ones. There are potentially some alternatives, but you'll see why we don't talk about other ones. Essentially, it's showing at what temperature is required for plasma to start, like fusion plasma. So you can see DT's start temperature is the lowest by a considerable margin, which is why it's favored. DD runs approximately 4 to 6 times hotter than deuterium fuel or deuterium tritium fuel. And since we already know how hot fusion plasma is, and you're multiplying that by 4, or in the case of proton boron, over 10, that's getting to stupid numbers. So it's much easier to engineer sort of reactors when you're using deuterium tritium, even with all the drawbacks of more radiation, how horrible tritium is, how much more tritium you need to produce. That's still more favorable than making a reactor which can sustain the temperature 4 times as much. And then you see deuterium, helium. You can see what the graph shows now. So here's our DT reaction. So we've got our deuterium and our tritium hit together. Got helium with 3.5 MeV energy out, our neutron with 14.1, which we've seen before. This is what DD looks like. So when you smash 2 atoms of deuterium together, you can get 2 isotopes of helium or tritium out, which then you'll have a neutron or a proton, generally with those reactions, a 50-50-ish % reaction rate. And you see you get 3 or 4 MeV out compared to our 14.1 on the other slide, which is showing that why you don't actually get loads more energy out of this one, even though you have to put loads more energy in. And you can almost ignore the percentage of the gamma rays, but potentially have massive amounts of energy. Deuterium helium is a very interesting one because this is aneutronic. I think that's it. So you've got helium and deuterium smashing together, and this one actually produces a combined 18.4 MeV, which is better than what we had for DT, but at the same time, you're looking at sort of 5 to 10 times the amount of energy in to actually get this thing started. And then potentially the most interesting one, so this one is also being paraded as neutron free. It's quite interesting because boron is very naturally abundant. There's much lower radiation for this one, but you can see the energy out is a lot lower. And because it has to run at such a high temperature compared to DT, it's much more difficult to avoid the energy losses. because if you lose a little bit, you're going to lose a lot compared to a reaction which is 10 times cooler, essentially. Most of these reactors that use this kind of stuff are much more complicated and much more highly engineered. We already know how complicated a lot of these already are. But if you want an example, we've got TAE Technologies in the US. So got a summary. I'm very open to questions after this. Yes, so there's many different ways you can do nuclear fusion reactor design. So it's not just we have our donut shape and then we're done. We can have a look at some crazy stuff. There's a lot of lasers you can have a look at. You can have a look at stuff that involves just shock waves. Stellarators, they're pretty good. They provide a lot of plasma stability, but the complexity of them increases and it's much harder to turn them into sort of reactors for the grid. But they have the higher potential, I reckon, than Tokamaks once we solve the problem, because you have plasma stability is really important. Initial confinement fusion, yeah, very dynamic and creative approach. If you want to learn about crazy like technology, that's the way to go. I'm pretty sure Bond villains have a hand in designing most of these reactors. But most of their experiments are also essentially unique. Whereas like Tokamaks, you can generally compare like for like. It's like, okay, there's a diverter here, here's where the breeder blanket is, yada, yada, yada. Whereas ICF is a lot, well, you've seen how different three of them are compared to like anything else. It's generally cheaper, but they've got a lot of other problems that come with. So it is favored by private investment for that reason. And then you've got some alternative fuels are possible, but despite how bad tritium is, because of the lower energy required to start the plasma, it's massively favored. And I'll meet with a week. Iman put one in again. So we are potentially now not going to go back to ICF or Stellarators. For our examples, we're just going to focus on Tokamak style and mainly on DT stuff, because that's the majority of what happens. It's also easier for us to stick to a particular thing that we talk about rather than, okay, well, we've done this radiation damage for this one, rather than going, oh, then we're going to talk about this for Stellarators and this for ICF and blah, blah, blah. But yeah, if you've got any questions, please let me know. Radiation damage is going to be next week. I think we're going to put 2 lectures on radiation damage because it is a significant limiter for designing lots of these things. But yeah, please let me know if you've got any questions. Thanks for listening. It's fine. Also, I have a question for Jamie Edwards on the chat. Are you the Jamie Edwards that I know? Because I know some guy called Jamie Edwards, but yeah, just text me. Right, go on. Questions?
So in idea, how do we literally not like explode and damage our reactor without finding?
That's a good question. So the explosions are generally sort of contained in a similar way. You'll have like a similar setup, sometimes like breeder blankets. That's why you also see a lot of liquid lithium lead flowing around these things, because it'll absorb a lot of the radiation damage. You can't damage a liquid. It also doubles for energy extraction. A lot of these are also consumable sort of bits, because you will blow it up and then you just fire another one. So it does create some waste that way. But the short answer is I'm not entirely sure, because most of these are still experiments and power plant design is still a bit of a way off. I couldn't get a good picture of what a power plant should look like. Otherwise, I would have shown you one. But generally, they're going to deal with it in a much similar way to how they do it for tokamaks. Got to remember, these pellets are the size of a pea, so they're not putting in as much fuel as a tokamak would have in one go. But yeah, it's a real big concern, especially the radiation damage. But they need that energy so they can extract heat, so they're actually going to have to tank it in some way, shape, or form. But that's why a lot of them do have liquid metal walls, because you can't damage a liquid, so it'll double as your energy extraction, and yeah, essentially.
Essentially, it's like where we control small explosions.
Yeah, they're not making a nuclear weapon blow up every single time.
Yeah, but what about the durability of the reactor itself?
Well,
Is it less durable?
well, arguably it's worse in lots of different ways. So I don't know if you've ever done any material science or materials for engineering and things like that, and failure mechanisms. So tokamaks will generally run at high temperature for a long time, so that you'll get problems like creep happening. Whereas for this, because it's bursts, you'll have a lot of thermal fatigue. So it'll fail that way because it's going hot to cold, hot to cold, hot to cold. So it's going to damage your material in that way.
What's the problem?
Creep.
Problem with that?
Creep is when you have something at not its melting temperature and not at its full yield stress, but it will deform because of the temperature it's at over time. Which is generally more of a problem when things are running hot for a while. So yeah, the reactors are in big trouble. A lot of them won't survive for very long. I personally found it very funny when the CEO of First Light Fusion, he was saying that his containment vessel would last for 200 years, which I think is just a lie. Because I know the material that it's made out of, and it's not a very good steel. It's good for fusion, but it's not generally good steel. And their only protection was a lot of liquid lithium. And it won't last that long. So I don't know what the scope is for like replacing parts. Like I mentioned, ITER, their plan to like replace at least all their parts like diverter once for their running of it. But I don't know what the plan is for all these ICF sort of reactors. I imagine they're going to be better in some aspects for survivability, worse in others. It'll be a trade-off. I think they're banking on the liquid lithium or liquid metal walls to protect from a lot of the major damage. But yeah, it's not going to be good. When does the Fuser project begin? I think we're planning to do that next month, aren't we? Mhm. Yeah. So fusers, they're not nuclear and they're not like there will be some crossover with like looking at plasma and like maybe the shape of it and vacuums and things like that. But they are quite a few rungs below what we've talked about. But I'm pretty sure they're going to do a workshop for you on making it, so they can probably talk to you about the different physics and stuff of that if you're interested. Any other questions? I'm aware of just like blasted through loads of different bits. So if you've got any other questions that you don't want to talk to everyone about, just feel free to email me. I'm constantly on my phone. So yeah, any other questions? No? Maybe?
Any specific benefits of that silicon cell?
Well, it almost feels wrong saying this, but it's a more proven technology. Because they've been designing these things for well since the 50s, whereas ICF is a lot less. It's only like sort of recently transitioned into sort of making energy out of it. They've ICF comes with its own set of problems which are almost unique to their reactor that they make because they're not similar to each other. Especially trying to keep a reactor going, like you've got to do at least like 6 to 10 pulses in a minute and all the mechanisms have to work properly, otherwise you're not going to get a net gain out of it. Your net gain has to be positive for every single pellet that you put in, pretty much. But they do have some benefits in the fact that yes, they're cheaper, and that is a massive advantage because you can test to destruction, right? They can't test E to destruction because they've only got one and they can only afford one. It's really taken them like 70 years to build the bloody thing. So like, no, okay, 50. But like, whereas these have like, you can get them online very quickly, test what you want to test. Okay, right, we've got that data out. Let's rebuild another one and try it again. Which is massive in this because pretty much anything that's been ever made has been tested to destruction. Like trial and improvement, right? I mean, in terms of advantages, they also will probably happier to run on deuterium fuel. So the startup isn't as bad for them because they actually don't need to start up and sustain a plasma. They just have to be hot enough initially just to implode it. Yeah, I feel like I've rambled a bit there, but does that sort of answer what you were looking at? Sort of. Something, and yeah, each reactor for ICF has its own individual benefits and drawbacks, pretty much. Like the NIF one with all the lasers, pretty good. Like that's pretty well tested. They've been testing that for years. And once they can figure out how to turn that into a proper reactor that will run, it's probably going to be fairly reliable. Lasers have got advanced quite a long way, so the actual startup energy needed for them isn't anywhere near as high as they used to be. Whereas the startup for a Tokamak is insane. Like the amount of stuff we had to go through actually just to start a plasma last week was quite a few steps, which required lots of energy. Whereas ICF, it's not, it's just bang, done. When the problem is doing that again and again and again. Yeah. But they're very cool. They are very cool. Unfortunately, we can't really stick to them. We're basically going to stick with the Tokamak because that's the most popular. So we're just going to stick with that for the rest of the course, I think. Yeah. I mean, just don't feel the need to stay, but if you've got any more questions, let me know.
How long did it take to build that?
Wendelstein, I want to say it started in the 90s. So about, let's call it about 20 years to get it up and running to a high standard. And then it's been offline 2 or 3 times while they've upgraded it. And those upgrades have made significant improvement. And they've basically taken it offline for like a year or so. Whereas Jet, when it was being upgraded, was off for like 5 years. It's yeah, Wendelstein's very, very good. It's a shame it's the only major example of a Stellarator. There are others, but it's the main one. Accelerators have a lot of potential. No, any more questions? I mean, feel free. Or just text me or whatever. I don't think we've got any questions online, have we? Yeah. Cool. All right, well, thank you very much. I'll catch you next week. All right, thank you everyone online. I'll see you later.